So this video is all going to be about over-extrapolation. Now, we're in the middle of a coronavirus pandemic as I record this here in Australia, and there have been a few cases recently. So I thought that what I would do is I would go back to some historical data and see if I can predict what's going to happen next with this current outbreak. So, we have data going back throughout the coronavirus pandemic in Australia, and here's a section of it. So this is real data that I got from this website down the bottom of the screen, and it shows that over a certain number of days, over a 2-week period, number of cases went up like this. Now I'm a data scientist, applied mathematician. I look at that and I say I can fit a model to that. In fact, I can fit an exponential curve to that. Looks like it's going to fit pretty well, and indeed it does. And so an exponential curve describes that data quite well. And then what I want to do is I want to say, well, I want to know what's going to happen next. I want to make a forecast about what's going to happen into the future. So let's take my orange line, my model there, and let's run it forward a week into the future. And I get some pretty scary numbers out. This is predicting that there's going to, in a week's time from now, there's going to be 9,000 people or so infected with coronavirus, which is scary. I said this is historical data, so I can actually go and look what actually happened in real life. And my model actually turns out doesn't look so good. If I go even further into the future, if I run the model forward another week, so predict 2 weeks into the future, it now looks pretty terrible, actually. And in fact, you might think there's something weird going on here, because 40,000 coronavirus cases, I think that's more cases than we actually have had over the entire over an entire year of the pandemic, and that's correct. What I was doing here is I fit this model to the first outbreak of coronavirus in March 2020, and what happened after those first few weeks very much did not look like exponentials. And if I go even further into the future, let's say I use my model to predict 2 months instead of 2 weeks. Well, now I've predicted that 10 times the population of Australia is going to be infected with coronavirus. So something's gone wrong here. I fit a statistical model that was pretty good, but I've used it badly, right? And the big mistake that I've made here was at this stage here. When I use my data to predict forward, when I use my model to predict forward, I got something that didn't actually look like reality. So I was doing a sort of out of sample prediction there, or an over extrapolation. This period from 15 days through to 22 days, that's called an over extrapolation. My data doesn't exist beyond 15 days. And so it's a bad idea for me to make a prediction that's outside of that domain. So this is something actually, this problem of over extrapolation occurs in a lot of places. Actually, there's a few different examples. One famous extrapolation that's been around for 50 years or so is called Moore's law, which says that the roughly computing power doubles every 2 years. And that trend has been going pretty well for 50 years or so. But most computer scientists say that this trend can't continue. And in fact, it can't continue. It's sort of bounded by the speed of light and by how many transistors you can put onto a chip. And actually, Gordon Moore himself, who came up with the law in the first place, doesn't predict that it's going to last beyond another 5 years or so. You can actually see that it's starting to turn over eventually, just because of fundamental limits of physics. There are more. Here's one that you might not have thought of. This is plotting the transatlantic crossing times, so the time it takes to go across the Atlantic Ocean as a function of time. So back in the 1700s, the Mayflower and Benjamin Franklin took 1,000 hours on a boat to cross the Atlantic Ocean. And if you were making a prediction about how fast you were going to be able to get across the Atlantic in 1750 or so, well, you'd say, based on these two data points, you'd say, well, this probably can't get any faster, right? You didn't know about airplanes then, and boats couldn't get across the ocean any faster. Then as airplane travel starts to exist, so Charles Lindbergh is down here, the travel times start to go down across the Atlantic Ocean. And so if you were going to make, at the turn of the 20th century, if you were going to make a prediction based on Benjamin Franklin and a few plane trips about how fast you're going to be able to get across the Atlantic Ocean, if you're going to predict 100 years into the future, you'd be saying that travel times were in the order of 100 hours or so. But once we actually have plane flight, that goes down very, very quickly. right? So history changed, and over the 20th century, saw a rapid increase in how quickly you could get across the ocean. But you notice, if you were even mapping to the predicting based on the 20th century, you'd be predicting, but by the year 2000, it'd take us an hour to get across the Atlantic Ocean. And actually, the times that it takes, of course, have plateaued because jets can't get any faster. And so until we have rocket travel, then and that model doesn't work either. So what's going on here at each stage, at each epoch here, I'm making predictions that are beyond the range, amount of data, beyond the domain for which I have data. Right? So I make these bad predictions because I'm predicting out of my sample, or I'm over-extrapolating from what I've seen before. Now, if you think that this is just a cooked up problem, this is just something I've cooked up and I'm sort of being devious by telling you things, well, think again, because here's actually an example from the journal Nature, where there was a brief communications that predicted, based on fitting curves to the 100 meter sprint times for women in the red and for men in the blue, by fitting models to those, linear models, straight lines, and then extrapolating those forward into the future. These scientists predicted in Nature, in the world's top journal, that by 2156, that women sprinters would be running the 100 meters faster than men, which seems like an amazing prediction. And it is. It's so amazing that a lot of people couldn't believe it. And actually, the criticism of this article, peer-reviewed in the top journal, came thick and fast. And in fact, some of these are excellent responses. So this one here says that the authors admitted to mention that if you continue this extrapolation even further, then by 2636, times of less than 0 seconds will be recorded in the 100-meter dash. So people going back in time when running the 100 meters. So that's good. My favorite is this one by a group of high school biology class, so students aged 16 to 18 in high school, who got to the core of the problem here, which is to say that these authors used a domain of 104 years to extrapolate to a domain of 252 years. So it's exactly that problem, that they took a domain that was relatively short, and then they predicted well outside of that domain, well beyond where they should. And that's the core of the problem. Now, as a piece of full disclosure, the original authors replied to the criticism, and they said, they appreciate the interest generated by this light-hearted piece. And a lot of the commentary about this suggests that the original authors were making a bit of a joke here. They knew what was going on the entire time, and this was sort of some grand joke being played on Nature, or perhaps a discussion piece. And if that's the case, then I wish my jokes would get published in Nature, but be that as it may. So the point of this, the moral of the story, is to say extrapolation is a fine thing to do. It's a perfectly reasonable statistical method to use, but we should only do it within the domain of the data. So within the 104 years that these authors in Nature use, it's fine to predict how fast people are going to run the 100 meters. Because I have data on either sides there, I can be relatively confident about that prediction. But outside of the domain of the data, extending past where I have data, is a very different story, and things can go horribly wrong. So this is a big problem in machine learning. It's related to the missing data problem. You don't have data from 2156, so you can't predict how fast people are going to be running then based on data from now. Now, if you think about this for too long, you might get a little bit worried. Every day since I've been born, the sun has risen at the start of every day. But I don't have data from tomorrow, and I don't have data from next week, from next year. So how do I know that am I doing the same thing? How do I know that the sun's going to rise tomorrow or in a week's time? Am I doing over-extrapolation there based on my experience? And the answer is no there, because while I don't have data from tomorrow or from next week, I have an awful lot of data about physics than about astronomy. The prediction that's actually being made there is a prediction about planets moving around due to the force of gravity, essentially based on Newtonian mechanics. And that prediction and all of the data for that has been around for hundreds of years, and we have understood that very well. So not all scientific predictions are bunk, but you have to be careful to think about what's the data that I have and what's the model that I'm using, and is it appropriate to make predictions from that data set. So predictions about gravitation, predictions about the sun rising tomorrow, very, very good, because we understand the laws of physics very well. Predictions about how long it takes to cross the Atlantic Ocean, very, very difficult, because to predict how long it's going to take to cross the Atlantic Ocean, I have to predict technological change, right? I don't have a model for that. That's trying to model all of human history, all of human civilization, or a technological process. So the two things are very, very different. And if we sort out what's my model, what's the data that I have, is it appropriate to make a prediction from this data, then you won't go astray.